Hey everyone, I hope you all can see me, and yeah, I think I can encourage everyone to turn your cameras on. I probably wouldn't be able to see you, but at least it will make the entire room a little bit more cozy and friendly if we can see each other's faces. I think I'm about ready to start. Yeah, I think it's 12:41 Brisbane time, which is 1:40 p.m. Sydney time. So if I didn't mess up with time, that's my session. And I'm going to talk about the serverless platforms. And my name is Illia. I'm a senior IT consultant, helping various small and large businesses, as well as startups. I'm also a mentor for Queensland government. I'm a mentor at the River City Labs, which is a local startup co-working space. And I would like to thank the NDC Sydney for this opportunity to present here. Over the last couple of years, I've been very lucky and I had an opportunity to work on a few cloud-based serverless solutions using AWS. And therefore, I would like to share some of my experience today and some of my knowledge I got over the last couple of years. I'll try to keep my talk platform agnostic, as many cloud providers offer similar things. And I've also done a bit of research and will present serverless services comparison from different cloud providers. Just keep in mind that my main expertise in AWS, and I think it's going to be quite challenging for me to get some immediate feedback, but I'm going to monitor your messages in this chat and maybe in Slack chat later, in Slack channel for the room too. And I will try to answer all your questions during my presentation or at the end. All right, so let's start. I think before we will dive into details, let's us take a brief walkthrough into the history. So traditionally, applications have been installed on bare metal servers, and therefore they couldn't be really decoupled from underlying hardware. It gave a lot of control over the implementation, but also required significant initial investments and a lot of effort maintaining and upgrading hardware. The development of virtualization techniques in late 90s and introduction of some modern hypervisors, such as VMware, allowed us to abstract the operating system from the hardware. So major cloud providers made the next step, allowing customers to think less about virtual machines provisioning. So they could just spin up some virtual machines in a few minutes. It's something like EC2 from AWS. In 2013, a Docker container was introduced, and it was, I would say, the beginning of operating system level virtualization. So it allowed actually to deploy applications in using a deployment technique called containers, and it allowed just to create some packages with all application, all dependencies, and ship them to the operating system. So basically, it allowed to abstract some operating system, and it also solved the problem when something runs on your machine but doesn't work on other people's devices or doesn't work in test or production, something that happens quite often. And I think the next step is basically serverless. And serverless computing delegates infrastructure provisioning, configuration, and management to a third party, such as Microsoft Azure, Google Cloud, or AWS. And initially it started with a thing called function as a service. And functions are basically just snippets of code that can be executed independently. And I think the beauty of this implementation that the provider decides when to create or destroy replicas of the software and will respond to increase load by creating more or less of these replicas, which makes them much cheaper. And those solutions, they're also very green because the underlying hardware is utilized way more efficiently. So it allows us to worry less about infrastructure and think more about the code. And with the time, definition of serverless expanded, and cloud providers started offering a bunch of other tools, such as event buses, queues, even the databases, or services to run something like Docker containers. So it all starts with a reason. And I think I would like to take a step back and consider a majority of questions that I'm getting from startup founders, from different clients as a technologist. And those questions are, why should we move to the cloud? Why should we use different programming languages like C#, .NET, Java, Python, Node.js? What is microservices architecture? Why should we use containers? Why should we pay for managed services? And why should we go serverless? And I think my favorite answer to all these questions is that people don't buy drills, they buy holes. So it doesn't really matter what do you use to make things happen. There is a great article by Ben Kehoe explaining that serverless is a state of mind, allowing to focus more on business logic, and the product value should drive implementation, not technology preferences. The chart on the screen is showing how modern deployment techniques help businesses to increase their focus on business value and decrease concerns about infrastructure provisioning. However, on the other side, it comes with less control over the stack implementation. And therefore, it's extremely important to know when and why we should use serverless by understanding its benefits and limitations. So I think quite obviously that the main benefit of serverless is that there are no servers to manage. So, well, we know that there are still some servers, there are still some operating systems, runtimes, containers, but they all managed by cloud providers. So there is no such thing for business as maintenance windows. Or we don't need to patch operating system. We don't need to install any updates, or we don't need to upgrade the software because it's not supported anymore. It's important to know that serverless is not just compute services, but also a bunch of other things like even API gateways. And that's why it comes together as a bundle, which makes a big benefit if you think about some networking, let's say. So built-in scalability is another benefit of using serverless architecture. There is no need to worry about scalability and load balancing. So you can see on the screen that an extremely simplified schema of traditional application load balancing. Let's say there are two clients. Each of them makes a simultaneous call or request to the server. Both requests are sent over the internet. They pass a firewall and arrive to the load balancer that redirects request 1 to server A and request B to server, or request 2 to server B. If there is a sudden spike in a number of requests, then some additional services, C and D, can be provisioned. Yes, there is a way to set up an auto-scaling groups that can handle server setup for you and create them in minutes, but it obviously takes some time and effort. So in a serverless world, if there are multiple simultaneous requests, then the vendor will spin up, run, and as many functions or lambdas as needed. The providers often use containers behind the scene, but we shouldn't really worry about them. So in our scenario, if there are more concurrent requests coming at the same time, then our serverless application will handle them as easily as one by creating just additional instances of our function. So, and as you can see from the table on your screens, major cloud providers allow at least 1,000 parallel executions, and they support automatic scaling. This means that your application will be able to process an extremely high number of requests just as well as it can handle a single request from a single user. And unlike traditional architecture, it will not be overwhelmed by sudden increase of requests. So basically, it means that you can build very scalable applications straight from the beginning. And that's where we find the next huge benefit of serverless platforms. It is a pay-as-you-go model. This means that you only charge for what you use. And the good news is that all three major cloud providers offer at least 1 million of Lambda executions per month for free. Yes, there could be some additional services that you have to pay for, such as API gateway, and they will increase the overall cost. However, most prototypes or proof of concepts can be built and released without infrastructure investments. So you will start paying for the infrastructure only after your application will gain some traffic and ideally will start generating some income. High availability is another, and resilience is another benefit of serverless. So for example, AWS Lambdas will run functions in multiple availability zones across multiple regions. So basically, it means that if there is a service interruption in one availability zone, then you're still fine because the function will just execute in another one. It's important to remember that cloud providers still have some issues with their servers. They're quite unlikely to happen, but they happen all the time. And sometimes entire regions can go down. And again, in a traditional architecture approach, you should think about creating maybe a failover plan, which might require provision of some backup instances. And then in case of some emergency or incident, the traffic can be redirected at any moment. It can be automated, but again, it comes with additional costs. You shouldn't really worry about them when you go serverless. Decreased latency is another advantage because there is no origin server, so the code can run closer to your clients, utilizing access points on a global scale. However, again, the implementation can be slightly different provider by provider. From the architecture perspective, I think serverless encourages the adoption of new mindset. And that's the nature of serverless. It's actually forcing developers and architects to design systems using microservices. So different components, they can be isolated and deployed independently, which means that the release cycle becomes much shorter because you only update one component instead of releasing the entire monolith application. And another benefit that each component can actually have its own runtime, can use different programming languages. Like one function can be written in JavaScript, another one in Python, or another one in C# with no issues. And I think the last kind of big benefit that I found is that serverless is awesome. Like in any area of business, you would like to work with very passionate and intelligent people. And I think including software development, it is actually important to be surrounded by those passionate people. And from my experience, everyone who was involved in some serverless solutions development and testing actually wanted to learn more, wanted to contribute, and was definitely more engaged. So I think your using serverless is making your company more attractive for proactive and talented engineers. Well, let's have a look at limitations. And I think the most known one is a cold start of functions. So the very first cold start happens when the first request comes in after deployment. Then the service needs to download the code, load the code and all dependencies, all modules, and run the code. After that, request is getting processed, the instance stays alive to be reused for subsequent requests, and in majority of cases, an idle instance lifetime is about 10 minutes for AWS Lambdas, 20 minutes for Azure Functions, between 5 minutes and 5 hours for Google Cloud Functions. And as for cold start duration, you can see some of the stats published by Michael Shilkov in the end of the last year. And he was talking about difference between different runtimes or programming languages. So you can see that it varies from a few hundred milliseconds to up to 10 or even like 12 seconds. And obviously, it is a noticeable difference, particularly if it's used for the customer-facing user interface. So it should be taken into consideration what programming language you use, whether it's compiled or not. And cloud vendors, they're all aware of this problem, and they are dealing with these type of issues. In the end of last year, AWS introduced a concept of provisioned concurrency that will allow to keep certain amount of functions initialized all the time. And Microsoft has done something similar, launched pre-warmed instances, but But unfortunately, they come with additional cost, because if you want to keep one of the functions always warm, you need to pay for that. Another obvious limitation is the stateless nature of functions and timeouts. Different cloud providers offer 9 to 15 minutes of maximum execution time per request, which might not be enough to complete a task, especially if your task is huge and you're dealing with gigabytes of data. Functions are stateless by design, so the next invocation doesn't know anything about the previous one unless a persistent storage is used. However, the use of some persistent storage, such as S3 bucket from AWS or let's say blob storage from Azure, comes with the next limitation, which is a bandwidth and input-output bottlenecks. Even though major cloud providers, they utilize extremely fast networks with extremely fast data transfers within their networks, they are still much slower than and less predictable than just solid-state drive mounted to, let's say, a virtual machine. Also, functions have a memory allocation limits. Like it's 3 gigabytes for AWS Lambdas. It's typically 1.5 gigabyte for Azure functions. I think it's 2 gigabytes for the Google Cloud functions. So the serverless compute services might not be suitable if you need to perform a calculation that requires more memory. Another limitation that not all programming languages natively supported. AWS supports quite a few, like Node.js, C#, Java, Python, Ruby, and Go. Azure Functions work with Node.js, C#, Java, Python, TypeScript. I think you can even deploy PowerShell. And Google supports Node.js, Python, and Go. So overall, you can see that only 2 languages supported by all platforms, namely Node.js and Python. Logs and monitoring is another, I would say, quite difficult and interesting thing. Because when we're talking about distributed services, you need to make sure that you have some sort of correlation ID that you can pass through multiple services. And the logs will not be very easily accessible. And that's why there is a bunch of different third-party tools or third-party providers allowing tools to analyze logs. And metrics come in, such as, I think, Elasticsearch, like ELK Stack or Splunk. And maybe another thing that I would like to highlight is the use of common code. Like if you need to share some code, let's say multiple functions require the same business or code logic. And in this case, if you're making some changes to one of these shared libraries, you need to distribute them to all affected components. And I think it's not necessarily a bad thing because it actually enforces some discipline. It forces developers and architects to build very independent services, which is a key to decoupled architecture. However, we know that in practice, sometimes it doesn't work that way. But I like what Sam Newman said in his book called Building Microservices back in 2014, that the evils of too much coupling between the services by shared code are far worse than the problems caused by code duplication. So I think sometimes you can actually duplicate a bit of your code, but make sure that your services are independent. So it's more about finding, I think, that balance, which is quite a significant challenge for system architects. And finally, serverless architecture relies on extensive usage of many different services, including the databases, messaging services, notification services, API gateways, authentication providers, which makes it actually quite difficult to migrate from one cloud provider to another. And that's why they exist, because I think all major cloud providers, they can actually see that if they only provision virtual machines, or something to run Docker containers, you can easily jump from one vendor to another. As soon as you start using serverless, you kind of get in some vendor lock-in. All right. So if you remember, I started this talk saying that serverless is just another tool that allows to make things happen. So let's define now when we can use serverless architecture and when we should avoid it. And I think I will start with a bit of controversial one, because I believe that serverless is great for web and mobile APIs. And this is mainly due to its scalability and latency. So it's particularly great for applications with unpredictable load or some predictable traffic surges. So for example, if you run an application which is used, let's say, by schools, then you can predict that a lot of traffic will be in the morning hours, and there will be probably not much traffic on the weekends or school holidays or public holidays. So the serverless architecture will actually allow you to not pay for expensive high-end servers to be fully utilized only for a couple hours a day. Another use case for serverless can be to integrate a bunch of existing APIs, exposing only one endpoint to the client. It's great for automated and cron services that don't require a server constantly running. So it can be also used to back up some databases or perform some CI/CD tasks, change the cloud configuration regularly, get some data from the third-party providers. Multimedia processing, it's probably one of the most common scenarios. So like if you Google what is the most typical use case for serverless, you will find this one. So when the file is uploaded to the storage service, something is getting triggered. The function does some file transformation, such as image trimming, resizing, and those lambdas, like those functions, will be easily integrated with a bunch of other cloud services, such as face recognition. So you can basically do a face recognition just writing a couple lines of code. Event stream, batch processing, it's all great for serverless because it lets you to utilize software from third-party provider and integrate with a bunch of different things like payment system, authentication providers, communication systems. So as soon as there is some sort of event is happening, you can go and set up some workers that will do a bunch of stuff based on the event. On-demand scaling is ideal fit for data collection workloads. So serverless architecture is resilient to large traffic spikes with minimal risk of losing data. And I'm going actually to talk about one particular implementation of this scenario shortly. Some non-complex IoT services like AWS Alexa skills or IoT Hub from Azure and other, they can be really good use cases for the serverless integrations. However, there is a caveat that if your system is used by thousands of devices sending one request per second, then it will become extremely expensive. And as I mentioned before, CI/CD pipeline is quite an interesting area for serverless implementation. So you can do some GitHub webhooks that will trigger automated tests, website builds, deployments, etc. Serverless is not great for things like predictable and constantly high system load. Then the use of functions can be significantly more expensive comparing to virtual machines. It's not great for complex and long processing tasks. So they actually the functions designed to execute small chunks of code. And in most cases, it's achievable. However, if your function has to make async calls to other APIs or download gigabytes of data, then serverless is probably not the best option. And parallelism can be also tricky. So it's not really possible to run multiple threads within one function. So you need to probably execute multiple functions that can run simultaneously and then somehow sync them. So as I said, there is a bunch of memory limitations and limited non-persistent disk space allocation. So if you need a lot of resources, high memory or lots of disk space to read-write lots of data into the backend systems, again, it's not going to be the great use for you. And we've also discussed a few limitations related to the cold startup functions. We know that cloud providers are working on that. However, if you have some SLA agreements based on the average response time, then you need to consider carefully what programming languages and runtime you use. All right, let's look at something more practical. I've been working on ingestion API, and I've been actually working on the business intelligence product. And I think At a very high level, for all business intelligence products, you need to get the data, process, extract some value, and present to a client via the website in the form of reports, dashboards, via the mobile app. And if anyone ever worked with business intelligence or artificial intelligence solutions, then you will probably agree that the quality of data is crucial. You wouldn't be able to train a model if your data is bad. You wouldn't be able to get any valuable data insights for business if your source data is wrong or inaccurate. So in our case, we receive data from more than 25 different data providers, and majority of data contains daily figures and coming in the morning between 5 a.m. and 9 a.m. Some of the data providers were internal, some of them were external. Some businesses had APIs, however, many of them offered in-venue solutions that could be accessed only by VPN. The maturity of this API could be also different, as well as authentication required. Some vendors just push some data via FTP servers or had their own FTP. For others, the preferred way was just to push encrypted data to the cloud storage, so we had to download it and decrypt. So basically, lots of different scenarios. So the business needs was to unify the process of data retrieval by creating a single data integration solution for all providers. It was also important to make sure that we receive only requested data, so vendors couldn't push any unexpected data sets to the FTP server or cloud storage. We also would like to verify the data sets before saving them into our data warehouse. So if some fields are missing or in the wrong format, then we would like to actually reject those files. Obviously, all data should be encrypted, in transit, and at rest. And also, we were looking to find a cost-effective solution to handle spikes. Because at that moment, we had many quite expensive virtual machines provisioned, and they were running 24/7, but they've been only utilized for a few hours in a day in the morning. So a few assumptions were made based on historical data, like we were expecting to receive 35,000 files daily. The average size of the file was 3 megabytes. The maximum size was 150 megabytes. And the load spikes were between 5 and 9 a.m. So because we were talking about daily data from previous day. So let's have a very quick look at the proposed architecture. I just want to show you how the serverless solution can be built. And it is intentionally simplified version of the workflow with the purpose to demonstrate way of thinking rather than the actual design. So first of all, we decided that it would be nice to control what kind of data we would like to receive by defining job requests, that's how we called it, based on a schedule. So we needed a scheduling service to read some job request schedules and generate actual data requests. It's a straightforward task. We decided to create a function. So we used AWS, so we created AWS Lambda that was periodically triggered by CloudWatch event. All job requests, then they were stored in a serverless NoSQL database called DynamoDB. So basically, CloudWatch triggers Lambda. Lambda generates some DynamoDB items, keeps them in the database. Then we would like to allow data providers' clients to retrieve such jobs requests via REST API. So basically, we just wanted to give them opportunity to read some stuff from our database. So in order to achieve this, we used API Gateway Service, which is another serverless thing, which triggers a Lambda, and that Lambda reads from DynamoDB and passes back to the client. So we would like also to secure that endpoint. So we used AWS Cognito for users authentication, which is another serverless authentication provider. And we use JWT tokens for all requests. The files that we were going to receive could be really large. So they could be like 100 megabytes. So they couldn't really be sent via HTTP API gateway because there is some payload size limitations. So in this case, it makes sense to actually upload files directly to S3 bucket, which is a storage service. So the access was provided also by Cognito identity pools, when the user could actually exchange that JWC token for temporary credentials to access the AWS resources directly and upload data to S3 bucket. As soon as file arrives to S3 bucket, it sends a message to the queue, which triggers a sequence of lambdas to read the file, check if this file was expected, update the job request status, validate the content, save data to staging tables in our database. So we actually used SQS service more like an orchestrator for different lambdas. However, step functions, I think, could be used as well as event bridge. But that's basically that event-based triggers. Obviously, when something goes wrong, and it can go wrong at any moment, we would like to get notified if, let's say, validation fails. So then we use the CloudWatch to keep all the logs, and also Amazon SNS, which is simple notification service, to send email notifications to the tech support. Or the SNS can actually call another Lambda, and that Lambda will publish or send some messages to our Slack channel. So we didn't want to build a distributed monolith. So we just ended up creating a bunch of microservices. And none of them actually knows about each other. So the only way they can communicate to each other is via some shared services. And those shared services, as you can see, it's like API gateway. So we have like one API gateway for all services, or SNS SQS, which is queue and notification services. KMS is just key management service. Route 53, it's for DNS configuration. So that's why they could all be deployed completely separately. And this should be really, the shared service is only service that is kind of coupled with others. And I believe that such an architecture will be very similar in other cloud vendors, with the only difference that the message broker will be like Azure Service Bus or Google Cloud PubSub service instead of SQS SNS. And I would like just to briefly mention the outcomes we had. I'd like to focus on performance and cost observations. So we have completed throughput and load tests. And in the throughput test, we just try to load lots of small files simultaneously. Unfortunately, there were some network bandwidth constraints related to the network throughput and latency. However, we could observe that as soon as file landed to S3 bucket, then it was processed in a few hundred milliseconds. So we have never seen more than 68 messages in the queue when we submitted 1,000 small files. The entire process involved 9,000 function executions. So basically 9,000 lambdas were created or invoked, did some stuff, and then ended. 5,000 DynamoDB read writes, 4,000 messages sent to SQS, 9,000 calls to S3 bucket. So it sounds like for 1,000 files, it took only 2 minutes, but a lot of calls were made. And in the load test, we were trying to load 3,000 large files of the size of 91 gigabyte. And on average, it took only 15 seconds to process a file, which is pretty good. And that's mainly based on the content validation, because the functions were run a bit longer because we're doing some JSON checks, etc. So I'm probably not going to dive into details. And we could see a small increase in terms of messages in queue, 75 messages, but not dramatic at all. And even though we were talking that we still required 38 different events to happen, such as calls to various services, lambdas, DynamoDB, etc., per session to process a single file, it still was fairly quick, and it was actually fairly cheap. So we were doing some cost estimation. We just picked a random client who was going to actually send us 40,000 files per year, based on assumption that, let's say, we have 100 customers per year, which is roughly 4 million files to be processed, which is 12 terabytes of data. And then we used the price for each service and intentionally didn't count free tier for our estimate. And as a result, we only got the variable cost like $462 American per year. and fixed cost was like $63 per year, and that's mainly for the DNS setting and some other guards. So it seems to be a great price for a cloud-based on-demand solution with a built-in scalability and availability. Because previously, to support the same thing, we had to run, I think, 5 virtual machines, and the cost was probably 20 times higher, at least 20 times higher. So it's been a great saving for the company. And if there is no transactions due to COVID-19 or something like that, then you don't need to pay for anything. There are only some fixed costs, but otherwise you don't pay for anything. And if you just get in a sudden spike, you're ready to scale up automatically at any moment. So what we learned by implementing our solution? I would like to start with the value of infrastructure as code. And this is probably what I like the most about cloud development. And I will be honest with you, I don't like reading documentation. I think nobody does, or they lie. I don't like documentation on how to set up an environment. The problem is that it often doesn't really cover everything, or not updated, or it was written for Windows Server 2003, and you are trying to configure similar things for Windows Server 2019. So that's why it easily becomes a nightmare, and it takes hours and days to actually deploy and test. So for this reason, infrastructure configuration definition files that can be used to set up environment is the best documentation ever, because it's self-explanatory. In our case, we just created a bunch of CloudFormation templates to build cloud infrastructure for all services using authentication service, error handling service, and others. So if you want to really know what's going on in terms of infrastructure for the error handling service, you just go to that YAML file and you can see clearly what's been created, why it's been created, what parameters they considered. So all templates, they take a few parameters. One of them is environment identifier. So each developer can create its own isolated environment that will be set up exactly the same way as integration, QA, UAT, prod, non-prod environments. And I think that cloud providers, they have a very strong support for infrastructure as code. And they actually start releasing more and more tools. Like AWS release CDK. Basically, that's something that actually helps you to create the entire infrastructure using TypeScript. All infrastructure changes should be deployed after the code review. And actually, in our company, we don't allow to make any changes via the console. So all changes should be traceable and easy to identify when and why something went wrong. That's why all changes should be made in the infrastructure files and committed to the GitHub repository or any other repository of your choice. And also it enables security as code. So security specialists can be involved in the code review process early, which is great because security concerns could be addressed early in the software development cycle. So they can have a look at your, let's say, how you create DynamoDB table, and they can say, oh, we basically require a different type of encryption. So it's great. You don't need to change anything after you release the production. You can actually do it straight away. The role of DevOps is different. I think as soon as you adopt infrastructure as code, then it becomes developers' responsibility. You cannot really ask your DevOps department to create a new queue or a NoSQL database table every time you need it, because you need it all the time. And that's why it's important that every developer now should understand the services they're using and their constraints. So if you're using DynamoDB, you should be familiar with DynamoDB, you should understand the constraints. It increases the importance of professional development for everyone in the team. And that's why I encourage actually everyone to start thinking about getting some certification, regardless of your role, whether you're a business analyst, a developer, a tester, or even a project manager, because everyone who is working on a serverless application now becomes a DevOps engineer. And the great thing is that it's not boring. and it helps to increase the level of engagement and commitment among team members. And this applies to QA engineers too. They are part of DevOps world, which is exciting, but it's also challenging. And we found that testing of serverless application is far more complicated because a lot of things happening under the hood. I found that unit testing is actually less valuable because you're trying to mock the behavior of cloud services. So that's why it's not really helpful just to write unit tests. And QA engineers need to be able to familiar with some login services so they can actually understand what's going on under the hood. They should be able to monitor the messages if you deal with SQS or queues, event buses. They should be able to test what happens to the messages, what happens in dead letter queues. And it is way more than just testing a user interface against expected results. So they need to have some command line skills, scripting skills, to be able to write some automated tests. And that's the good news, because those challenges, they actually encourage to adopt automated testing practices. And another important lesson we learned is that automated CI/CD pipeline are required for serverless applications. So for those who are not familiar, CI stands for continuous integration. CD means continuous delivery or continuous deployment. And continuous integration is basically a practice when all developers commit the code changes to a shared code base, and the automated pipeline can immediately build the code, run unit tests, identify some issues if there are any. And continuous delivery means that the artifacts from the previous stage can be automatically get deployed to a staging environment. Acceptance tests can run there, ensure that functionality is working as expected in a similar to production environment. Continuous deployment can actually automate even deployment to the production environment. So the serverless deployments are very sensitive, and they can be quite challenging due to the decentralization of cloud services. So additionally, there are many restrictions related to the cloud services to prevent the loss of data or the accidental loss of data. So for example, in AWS, you cannot delete an S3 bucket unless you clear all the files from that bucket. And that's why when you have your deployment script, you need to incorporate all this logic. So you need to do some checks. Is your bucket empty? If yes, you can delete it. So we created just a lot of deployment configurations as a set of CLI commands. And we also did code review of these pipelines. So basically, we just created UML diagrams. If that happens, then we should do that, etc., etc. And one of the most common issues I have seen related to deployment automation is that the process is defined by one person, and no one really knows how it works. It just works. However, the second opinion is extremely important when it comes to serverless applications deployment. Because we're talking about dozens of different services with their own specifics, and it's always good to have someone else to have a look at what actually you're trying to achieve. That's why I encourage everyone to have some mandatory code reviews of deployment scripts. And they should be also tested by QA engineers. So in terms of implementation, we tried a bunch of different tools. We just ended up defining our CI/CD process as the one that you can see on the screen. Our repository contains application code, deployment script, CloudFormation templates, and automated tests. So CloudFormation templates with all services defined here. And automated tests, they're basically a mix of some CLI commands and human tests that were sent to the GoCD server. And the GoCD server was just running that CloudFormation, the PowerShell script that was just preparing the deployment, created CloudFormation templates, deployed everything, ran automated tests. And the GoCD agent was also created in a serverless container. So with all these like 3 steps, and the beauty of this solution was that the GoCD agent was removed after successful deployment. So again, you only pay for what you use. Just to summarize the main points we have discussed today, that serverless is considered as the next stage of the system development deployment techniques after virtual machines and containers. All main cloud providers invest a lot into serverless space. And this area is expected to grow further. And we have talked about why we should consider serverless. And it's not about the technology itself. It's about increased value on business value, or increased focus on business value. There are still many limitations of serverless that we should be aware of. However, for some use cases, the benefits such as scalability, cost effectiveness, and high availability outweigh disadvantages. Infrastructure as code is great. It increases the quality of deployment significantly. I think early involvement of QA engineers and security teams is very beneficial. On the other side, it requires a good understanding of cloud platforms by all parties involved, not just DevOps. Everyone is DevOps now. And in fact, developers create code and infrastructure side by side. So testers need to be able to test all services under the hood, including some message brokers, dead letter queues, logs, other. Please invest into CI/CD pipelines development. It will pay out because properly configured pipelines allow to create and delete entire environments in just minutes. Like if you need to create an environment for penetration testing, you just can spin it up in like 2 minutes. And then after the testing, you can delete it. Each developer can have its own completely isolated environment. It's really beautiful when it's created in the right way. Deployment scripts should be reviewed and tested because serverless applications can be very fragile and they integrate dozens of different independent services. So it's actually important to avoid any manual interventions via the web-based console. Keep all configuration scripts in the repository, enforce code reviews for deployment scripts and testing. I think that's all I'd like to share today. Thanks for being here. And I'm just going to check if we've got any questions, or yeah, feel free just to